Okay, this video is on sex-linked traits. So this would be another example of non-Mendelian inheritance, meaning that the autosomal inheritance or the non-sex chromosome inheritance that we get from, say, plant height or pod color, anything like that that Mendel looked at, they didn't follow these inheritance patterns. Okay, so far we've learned about simple dominance. Okay, of course we spell it right. We have simple dominance, which says if you have a dominant allele, it will be expressed. Even if you have another recessive allele, that just means you're heterozygous, but you'll still express the dominance trait. Okay? Codominance, that's when you would have, if there's more than one dominant allele, they are both expressed if the phenotype represents both alleles being present. Okay? The AB blood type would be the example. Okay? We have incomplete dominance. And that is when you have a blending of uh, the two phenotypes to form a new phenotype. So kind of a good way to look at this is incomplete dominance has a heterozygous phenotype, okay, versus when it's complete dominance or simple dominance, like the first example here, okay, if you have the dominant allele, the recessive allele isn't expressed, okay. The codominant is both dominant alleles are being expressed if they're there, and the incomplete is it's a blending of the two different phenotypes, okay, or more, but for right now we're just looking at two, okay. The last type of non-Mendelian inheritance is going to be sex-linked. Now, the reason why we talk about sex-linked is because A, there's a lot of different diseases that go around that are inherited by sex-linked, hemophilia, um, male pattern baldness, okay, color blindness, okay, red-green color blindness. Those are all sex-linked traits, and the idea of sex-linked doesn't mean that, oh, if you have sex, you're going to contribute, you're going to inherit these. Well, if that was the case, then everybody would have sex-linked because you're not here unless some people have sex. So the sex-linked traits are referring to the type of chromosome, okay, which means I'm looking at which chromosomes. I'm looking at the X and I'm looking at the Y. All right. These over here, the ones I was looking at mainly were the autosomes, which are the other chromosomes that aren't sex chromosomes. Okay. Now, in many cases, the X chromosome is the one we're really going to focus on, just because, like I said earlier, the Y chromosome pretty much just tells you that you're no longer female and you're a male now. Okay, there are very few Y-linked traits. Okay, so I mean, Y-linked traits, X-linked traits, those are both collectively known as sex-linked. Okay, a vast majority of sex-linked traits are X-linked traits, not Y-linked traits, but I will give you examples of both. Okay. Now, the Punnett squares for X-linked traits or sex-linked traits are usually very similar. Okay, they're monohybrid, and I'm going to have a set symbols on the top and on the side. I'm probably going to put them on the. We'll go X and Y on top, and we'll go X and X on the side, because the whole idea of this is we're looking at these particular chromosomes. So I'm going to put the X chromosome here and the X chromosome here. Remember that this right here is representing the gametes that the mom can give off. This up here represents the gametes that the dad can give off. He can either give off the X or he can give off the Y. The mom can either give off one X from the X that she got from her dad, or she can give off the X that she got from her mom. In either case, she's going to give an X. The male will give either an X or a Y. Right now, what we're going to do is we're going to look at an X-linked trait, okay, known as red-green color blindness. And usually what that means is people who have red-green color blindness have a difficult time differentiating between red and green if they're right next to each other. In fact, in some cases it's said that they kind of see a grayish color that's in between. It doesn't look red or green. Okay? And that gene is carried on the X chromosome. So what I'm going to do is I'm going to turn this uh, good black X chromosome into a bad red X chromosome, and then we will fill out the table. Oops, it's not that way. X, 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 Y, okay, Y, X, and X. So we fill out a Punnett square just like we do in all the other Punnett squares that we did. Now, what we need to note is the interpretation of this Punnett square. So first thing I should see is I have two males, two females, right? Here are my males, right? Here are my males, and here are my females, right? If you look, three of these four, okay, specifically these three, they are not going to exhibit color blindness, okay? This guy, unfortunately, will. And the reason why this right here is going to be a colorblind male and this one is not is because this one has the bad X. Okay? This one up here doesn't. It has a good X, or he has a good X. He's not going to express that bad trait. Okay? They all follow the same inheritance pattern as far as red-green color blindness or hemophilia. I'm just picking red-green color blindness right here. Okay? This one right here, okay, in the first quadrant, she's not going to be colorblind because she only has good X's. Okay? This one down here in the third quadrant, she is also going to have normal vision. She is not going to have the red-green color blindness because she has a good X. Okay, because she has that good X, it's going to kind of act like a dominant trait, and it's going to act like a dominant allele, and it's going to overshadow the X. Okay, which means this red X right here is not going to be expressed in this particular female. But what that does is it turns her into a carrier. So she, okay, this little girl right here, she is a carrier. He has it, and these two up here, they are, for lack of better terms, normal. Okay? So whenever one says, you know, whether it be red-green color blindness or big one being male pattern baldness, um, it's not exclusive to males, so to speak. But if I have male pattern baldness, I didn't get that from my dad. I got it from my mom because my mom is the one that's responsible for giving me the bad X. Okay. Could my dad have given me the X? Sure. But could my dad have given me the X? No, because he gives me the Y. Okay. But it is possible for because of this, like for example, if I was to make a Punnett square with these two individuals right here, okay, and I'll go ahead and do that real quick. Okay, so typically this Punnett square where I bred somebody a male that had, so say this X is now meaning, instead of red-green color blindness, now it means male pattern baldness, okay, because they both follow the same trait or inheritance pattern. So this male up here, the father, has male pattern baldness. The mom is a carrier for male pattern baldness, okay? Guess what? This female right here is a carrier. This male is normal. This male has male pattern baldness, and so does that female. So it is possible for girls to get male pattern baldness, and this would be an example of how. Okay, but this is how X-linked traits are inherited. Okay, and usually how it goes is moms, and this is a rare occasion right here. This one right here is the more common one. Okay, where it's the mom that gives the male or the son. The mom gives the son the disease, not the male or not the father. Okay, so usually when it comes to X-linked traits, usually mom gives it to son, okay, and then son will give it to daughter, okay, and then daughter who becomes mother, is a carrier now will give it to possibly their son. There's a, you look right here, there's a 50% chance. Okay, if you look at these guys right here, let's go ahead and choose a different color. There's a 50% chance that the boys will have the disease. Okay, there's a 25% chance that the offspring will have the disease, but there's a 50% chance that if it's a boy, they'll have the disease. Okay, but this is how it works with X-linked. Okay, for Y-linked, it gets much easier. So if I have X, 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 and then my bad one is Y, X, 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 Y, Y, well, the father gives it to both of his sons, okay? And it'll always be that way. So pretty much if you have a Y-linked disease or a Y-linked trait, it's given to every single male in that line, because father, this is Y-linked, father will give it to son, who will give it to his son, who will give it to his son, and then because that's the only thing he can give if he gives it to his son. He can only give a disease Y. He can't be like the female and give partial, okay, or give one X or the other. It's the only Y he has to give has the disease, which means every male in every subsequent generation will have the disease. Okay? So that's sex-linked traits. If you guys have any questions, make sure you ask.